All right, welcome to section 5.3. We're going to be doing something called the fundamental theorem of calculus. And it's kind of a long thing to write. So I'm just going to be writing FTC for short. The fundamental theorem of calculus. Okay, and it's called the fundamental theorem of calculus because it links the two branches of calculus together. All right, so we can take a little trip down memory lane and remind ourselves of what the two branches of calculus are. In chapters 2 through 4, we focused on limits, which led us to derivatives. So that was your differential calculus. And we learned about rate of change, which is like velocity. And we also saw that derivatives were slopes of tangents. And that makes sense because, slopes are rate of changes. Okay, so that's the main thing of chapters 2 through 4. And then in chapter 5, where we're at now, we're looking at integral calculus. And then now we're dealing with area under a curve. And it turns out, and we also looked at applications of area under the curve. We saw that, it could help us find the distance traveled when given the velocity. But what we're going to see is that these two processes are actually inverses of each other. And that's what the fundamental theorem of calculus does. It links those two together. Inverse process. Okay. So there's actually two fundamental theorems of calculus. We're going to look at the first one. And what the first one does, it defines the area under a curve as a function. All right, so we're going to introduce right now the fundamental theorem of calculus number 1. And to do that, we have to introduce the area function. And the area function is called g of x. And we define it to be the area under f from a to x. Okay, so if we had a graph and we had our function f that starts at a, it goes to b. F is actually a function of t in this case, so we can introduce another variable x, okay? And what happens is x is a variable. X can be any number between a and b. Okay, so for instance, let's say we're defining x to be right there. All right, so then the area from a to x under f, so that region, that's what your g of x is. And it changes, right? As we move x to the left and to the right, closer to b, closer to a, g of x is going to change. So g of x is indeed a function. And g of x is the area under a curve of f. So we know the area under a curve is an integral. So this is what g of x is, all right, for f of t dt. It's the area from a to x of f. Okay, so let's do a little exploring about g. So again, all we've done is define g to be this area function. So what are some things that we can discover about g? So we're going to do a little exploration. And from section 5.2, number 27, we discovered that if we were to take the integral from a to b of x dx, okay, and we did that. If we look at a triangle, we can figure out the area, right? We can figure this out by looking at, adding the area of the rectangle and adding the area of the triangle, okay? And if we do that, we're going to get b squared minus a squared divided by 2, okay? So relating that back to our g of x function, so then g of x, let's say our starting point was 0 and b was x. Instead of x dx, it has to be in terms of t, so t dt. That's going to be equal to, let's see, so in this case, x is b and 0 is a. So it's going to be x squared divided by 2. All right, so just substituting into that formula. And then, of course, we can picture that on a graph. So this is, the function f of t equals t. And if we go from 0 to x, we're saying then that this area is g of x. Okay, well, there you go. All right, so what's next? Oh, and then, we can even do it just using the region, right? This is the area of a triangle. The base is x. The height is x, because that's what the function is, right? X equals x, or f equals x. And then the area of this would be x times x, 1/2 x times x. So that's how we get it, 1/2 x squared over 2. Okay, so I want to do this. We just said that, and I'm going to write everything in terms of x's. I'll use a different color because this is our thinking, our critical thinking step. So we just said f of x was x, right? I'm just changing the variable. We're allowed to do that. And g of x is equal to x squared over 2. So that's what we got from this. And can you see how these are related? Well, what happens if we take the derivative of g of x? Let's see, bring down the 2's cancel, and we're left with just x, which is exactly what f is. Okay, so there you go. So let's do this. So let's explore. This is going towards, the fundamental theorem of calculus, part 1. Let's find g prime of x in general. So in general, not just when f is equal to x. Let's find the derivative and see if that can give us any information about what our area function is. Give us any information on this area function. Okay, so in general, for this, let's find that derivative. Okay, and we're going to do this using the definition of the derivative. Do you remember use the limit definition of the derivative? So going all the way back to chapter 2. Again, fundamental theorem of calculus, it's bringing everything together. That's why it's fundamental. Okay, so let's look at a picture. Here's our f, okay? We're going to go from a to b, kind of like always, right? And then x can be some variable in between a and x. And we know that that first region right here, this is what we're calling g of x. and we want to find that derivative. So what we're going to do is this. We're going to, just like we do with limits, we're going to add a little bit of h to x. So x plus h. And we're going to create this rectangle. Okay? And we're going to figure out the following. We're going to look at g of x plus h. Okay, so that's the area under the curve from a to x plus h. And then, hold on, I want to draw that shaded region a little bit better. Let me see if I can do that. Okay, so we have this rectangle, and we're going to first consider this part right here. So the area under the curve. We'll talk about the rectangle later. Okay, so to figure that out, we're going to look at g of x plus h, so the area of this whole thing, and then we're going to subtract the pink. And that's going to leave us with the blue. So it's going to be g of x plus h minus g of x. And this is the area under f between x and x plus h. Okay. So there you go. So if we have a small h, we can approximate it using that big rectangle, right? The larger rectangle right here. So for a small h, we know how area under a curve works. We can start by estimating the area under a curve by using lots of rectangles. So let's do that. Let's create a small h. So this is our h right here, h. Use a rectangle to approximate that part in blue. This area right here, which is this, g of x plus h minus g of x. And it's going to be approximated using that rectangle, all right? And we have an h, and we're saying that the height is, yeah, I created it. I used this endpoint, which was f of x. All right, so we approximated it using a right endpoint rectangle. All right, so look at what I'm creating here. This is awfully clever. I'm going to divide both sides by h, and then this expression on the left should look familiar. Kind of looks like the derivative definition. And it would be the derivative definition, but what do we have to do with this h? We have to get it closer and closer to 0. So at this point, we're going to take the limit as h approaches 0 of this expression. All right, and then as that goes to h, as h gets closer and closer to 0, right, these two things eventually equal each other. So this is also going to be equal to the limit as h approaches 0 of f of x, which is just f of x, because there's no h in our function f, okay? And now what is this expression right here? That's the limit definition of the derivative. And so we're saying then that g prime of x is equal to f of x. Okay, so that gives us a little insight into how the area function is behaving. And actually this result, this is what the fundamental theorem of calculus is, part 1. All right, so let's write it out. So that was our proof of the fundamental theorem of calculus, how derivatives are related to areas. So fundamental theorem of calculus, part 1. So we have, if f is a continuous function, on a closed interval, a to b, then the function g defined by the following, the area function. So same definition we've been using before. Oops, hold on, I'm going too fast. Upper limit is x, and then ft dt. There we go. For x between a and b. This is continuous and differential. Okay, and the big part is what we just showed, that g prime of x, if we were to take the derivative of this area function, it's just the inside. Okay, so we're really seeing how taking the derivative and taking an integral, or derivatives and integrals, are inverse processes. So for instance, the derivative of an integral is almost like the identity function, right? It just gets us back to f of x. Okay. So let's practice the fundamental theorem of calculus. Part 1, of course, right? All right, so we're going to find the derivative of the following. We're going to find the derivative of g, and g is defined to be the integral from 1 to x of the natural log of 1 plus t squared dt. Okay, notice we are filling the criteria, right? We're going from a is a constant, so constant to x, a constant to x of some function. Well, if we take the derivative of that, we're just going to get the stuff inside. So according to the straight application, direct application of the fundamental theorem of calculus, this is saying that the derivative of g is this f, right? So remember, this is your f of t. All right, but we changed the variable to the x. So this is natural log. It's no longer 1 plus t squared, but it's 1 plus x squared. And there you go, right? Almost too simple. So let's look at something a little bit more intense. So let's define h. We're going to find the derivative of h, where it's no longer constant to x, but it's constant to, let's say, root x. Then we have of the function z squared plus z to the 4th plus 1 dz. All right, so it's no longer of this nice format, right, where it's going from constant to x. It's going from constant to root x, a function. So this is what we're going to do. We're going to make this root x look like a single variable. And we're going to do it with the u substitution. So we're going to let 1 root x become 1 to u. All right, and then we have z squared over z to the 4th plus 1 dz. So now we can use the fundamental theorem of calculus part 1. Okay, but this is the thing. So h prime of x, that's dh dx, right? Just another way of writing it. But this is no longer going to be an x, it's a u. So we are actually going to be using our chain rule. We're going to take the derivative of h with respect to u first, and then times the derivative of u with respect to x. Okay, so for instance, up here, with our u equals root x, then du dx is going to be 1/2 x to the negative 1/2. All right, so we take the derivative of that u function. So now this is what it's going to look like. Okay, and again, this is the chain rule. Chain rule. Okay, so you can write it like this. You can also write it as just primes. Some people like to work with primes instead of this notation. So whatever floats your boat, okay? It's potato, potato. But, goodness. Let's fix this, guys, too. That's not the derivative. That's still h. This is still h, okay? And then this is h prime. So when we take the derivative, again, the fundamental theorem of calculus is telling us it's going to be this, u squared plus u to the 4th plus 1. That's the fundamental theorem of calculus. To the 4th plus 1. All right, and now we know u prime of x is this. And remember, if we're trying to find the derivative of h with respect to x, we have a bunch of u's. So what do we have to do? We have to resubstitute u with square root of x, right? That was the original one. So let's make those substitutions and clean it up, and then we have our derivative. All right, so it's going to be root x squared. So x to the 1/2 squared. And then it might be easier to write it as x to the 1/2 when we're taking the 4th, because then we can see 1/2 times 4 is 2, so it's x squared. So a little bit easier, whatever floats your boat. Okay, so we're looking at x on the top divided by x squared plus 1 times 1 over 2 root x. Okay, and then, we can, so many different ways of simplifying. We can cancel, let's say this is x to the 1/2, so we can use our exponent rules. 1 minus 1/2 is x to the 1/2 on top. So that cancels, then we're left with 2 times x squared plus 1. So that's a nice way of simplifying. So we'll just leave it at that. All right, so that one we had to use the fundamental theorem of calculus, and we had to use the chain rule. Okay, so let's try some more examples. You guys can try these on your own. There are number 12 and number 14 from the homework set. And you're going to find the derivative of r if r equals this. Okay, and notice the limits of integration. It's supposed to be constant and then variable, and it's not that. So what do you think you can do to make it constant then variable? So think about that. And here you're going to find the derivative of y. Looks like you're going to have to use the chain rule too. So go ahead and push pause and then come back and look at the solutions. Okay, so for number 12, before we find the derivative of r, we can switch the limits of integration from y to 2 to y. And then what do we have to do? Make it negative. That's one of our integral properties. So that was an easy fix. And now we can use the fundamental theorem of calculus. When we take the derivative of y, notice they match y and y. That's perfect. It's going to be negative and then y cubed times sine y. There you go. And that's it. Number 16 is more involved because we don't just have an x. Right here it's x to the 4th. So what we could do is make a u substitution where u is equal to x to the 4th. Okay, and then y prime is going to be y prime of u, right? So like the fundamental theorem of calculus, but then we have to use the chain rule. So we'll have to do u prime of x. All right, and that's not too bad. U prime of x is going to be 4x cubed. All right, so let's see how that pans out. This first one is the fundamental theorem of calculus part 1. So notice the variable u, so it's going to be cosine squared u. And then this next one is that substitution we had, 4x cubed. All right, and then final step, we'll want to resubstitute back. So we'll want to say that u is x cubed, x to the 4th, excuse me. Put in parentheses. And I'll just move that 4x cubed to the front. All right, and there you go. So some quick applications of the fundamental theorem of calculus, part 1. And then let's look at something that's a little bit similar. It's a little bit more intense. And then we'll move on to the fundamental theorem of calculus, part 2. Where are we? Oh no, I changed my mind. Let's move on to the fundamental theorem calculus part 2 now, and then we'll look at more examples after.